All right, everybody, welcome back. We will have one more example now of Stokes' theorem. So let's let C be the triangular curve in three-dimensional space whose vertices for the triangle will be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. And on this curve, and let's see, also it's oriented in such a way that you go kind of around this way, like that. Okay. And so on this curve, let's consider the vector field, big F, whose first component is x plus y squared, his second component is y plus z squared, and his last component is z plus x squared. Okay. Now notice that if we wanted to do the line integral of f along this curve C, we'd have to do it in three pieces, right? Because we have these kind of three distinct straight line segments. So if we would need to parameterize each one separately and then ultimately compute three line integrals. Well, maybe that's a little bit much for us, and we would rather instead just trade this line integral for the surface integral of the curl of f instead, using Stokes' theorem. So the surface that's sort of bounded by C is this triangular shape here, right? This comes to us, this is kind of just like a little piece of a plane, right? A little piece of a plane that kind of juts across here. And so we know the equation of that plane. And so we can probably parameterize this surface pretty easily and trade the line integral of f for the surface integral along this nice surface S of the curl of f instead. Okay. Now notice that plane is really, since those three vertices are 1, 0, 0, 0, 1, 0, and 0, 0, 1, you can see that the plane is really x plus y plus z equals to 1 is that plane that we're just cutting a little bit of triangular portion out that gives our surface. Another way you could see that is just do the sort of standard exercise. Given 3 points on the plane, you can get the displacement vectors, get two displacement vectors that live on that plane, and then compute their cross product, get a normal vector to the plane, and do the sort of standard way you find the equation of a plane. But this one's a little bit easy that we don't have to think too hard. We can just see that this is the equation that has to be satisfied. Okay. And we're really just looking for the part of that plane that lives in the first octant of three-dimensional space. And so really, with just solving and letting z equal to 1 minus x minus y, we can really see that's just the graph of this function, f of xy equals to 1 minus x minus y. And if we were to take that graph and look from the z-axis downward and sort of project to the xy plane, what we would see is a sort of right triangular region where x goes between 0 and 1, and y goes between 0 and the line 1 minus x. Okay? Okay, I think we've seen this before. I think it might have come up on exam 2 or something. So we can parameterize that surface, that little triangular portion of that plane, by this easy parameterization using the fact that we have a graph of a function. So we'll let x be in the first coordinate, y be in the second, and 1 minus x minus y be in the third one. Where again, x and y are going to vary over this triangular region D of the xy plane. So then computing the sort of tangent vectors to our surface are going to be s sub x will be 1, 0, minus 1. And s sub y will be 0, 1, minus 1. And taking their cross product gives us that the cross product sx cross xy is, let's see, 1 in the first component, and 1 again in the second component, and oh my gosh, 1 in the third component again. So the normal vector field to this plane is actually a constant vector field at every single place xy, or xy comma 1 minus x minus y. We get this vector here, 1, 1, 1. That's the normal vector that is at least consistent with our orientation here. So if you're moving right-hand rule-wise, if you are moving your fingers in the direction of this blue curve so that they are curling inwards towards the gray surface, your thumb will point in the direction of these normal vectors sx cross xy. Now notice another thing too is that since we knew that this triangular region came from the plane x plus y plus z equals 1, you could have read this normal vector off immediately from the equation of the plane, right? And the fact that it's a constant vector field that's the normal vector field, shouldn't be surprising because, as we saw before, that sort of normal direction to something flat like a plane is not going to change as you move around that object. Okay, so that's kind of a good way to tie in, something from way long ago, picking off a normal vector from an equation of a plane and doing it this totally different way of parameterizing the surface first and computing the normal vector field by taking the cross product of two tangent vectors. Okay, so now let's compute the curl of f, since that's the thing that we're going to want to do a surface integral of. And so we can see here in the first component, we will get 0 minus 2z. In the second component, we will get 0 minus 2x. And in the third component, we will get 0 minus 2y. Okay. And so evaluating this vector field along our parameterized surface, little s of xy, we can see that in the first component, we'll sub in for z, we'll sub in 1 minus x minus y. So we really get minus 2 times the quantity 1 minus x minus y. And then subbing in x for x gives us this, and y for y gives us the same things in the last two components. Okay. And now taking the dot product here, sorry, I didn't make that dot product symbol as big as I probably should have. So I'll fix that on the slides, but I'm not going to fix it in this video. So if we take the dot product of this vector field with the normal vector field that we computed, which was just 1, 1, 1, what do we get? Well, we get minus 2 plus 2x plus 2y minus 2x minus 2y, which gives us minus 2. All right, so everything else cancels. And sorry, I don't know, I guess I put this period here sort of prematurely. Sorry about that, so that doesn't belong there either. We just get minus 2. So now this is the function that we're going to integrate over the surface S. So that's easy. It's a constant function, right? So really now we are computing the to compute the surface integral over S of the curl of f. We're really just computing over the region, that triangular region D of the xy plane, the integral of the constant function negative 2. Now, I'd like to call out that there's sort of two ways to do this integral. One is that we'll just do it the way that you would normally do it. Okay, we set up our bounds here, we put our function down, we integrate first maybe with respect to y, and then we get minus 2 plus 2x. When we do that, that's very nice. And then we'll integrate with respect to x. We get minus 2x plus x squared and evaluate at 1. And what do we get? Minus 2 plus 1, which is minus 1. Very nice. Another way that we could do this integral, though, just from right here, notice that you can yank out minus 2. And this becomes minus 2 times the double integral over d of the constant function 1. And if you go back and look at that triangular region D, you'll see that it is a right triangle with base 1 and height 1. So its area is just 1/2, right? 1/2 base times height. And we know that the integral of the constant function 1 over d should compute its area. So really, we'll just have to take that area and multiply it by this now outside scalar, minus 2. That would also give us minus 1. So be sort of on the lookout for examples like that, because I really do like to give people examples like that, where once you've invoked the theorem in question and done the sort of relevant setup, that really all you're asked to do is take an integral that should just give you a scalar multiple of the area of the region of integration. So that actually computing an integral becomes like unnecessary if you know how certain things areas work. So, all right, so I think, okay, right, so that's it for that example. But now I want to call into attention one more thing here, the link between Stokes' theorem and Green's theorem. So suppose that we have a simple closed curve in space that lies entirely in the xy plane. So it's just flat in the xy plane somewhere. Okay? Then we can always make a surface that, that also lives flat in the xy plane and has boundary equal to that curve C. And so if we have a surface lying flat in the xy plane, then we can always pick the direction vector k that goes 1 in the z direction. That will always be normal vectors. So in fact, that vector put down at every single point of our surface gives us a normal vector field to the surface. Okay, but then if we have some other vector field, big F, on space, then to compute the surface integral over our surface of the curl of this vector field, well, recall that the third component, that's what we get when we take the dot product of curl with k, we get the third component of curl of f. But recall that that was exactly the integrand from Green's theorem. So then Stokes' theorem will say that the line integral of f along that boundary curve C will equal to the integral over that surface S, which is now itself a two-dimensional region flat in the xy plane, of this function, the partial derivative of q with respect to x, minus the partial derivative of p with respect to y. So that Stokes' theorem is really just a generalization of Green's theorem to vector fields that are no longer flat in the xy plane, but live generally in curved around in three-dimensional space. All right, so that's kind of clever. So we will have one more big theorem to meet for this semester, and then we will get to kind of sit back and look at them all from 1,000 yards and see how they all kind of fit into the same larger picture. So stick around for the last one of those theorems next time.